Looking at section 2.4, we're going to be doing some dividing of polynomials. We're also going to look at the remainder and the factor theorems. So the first thing we're going to look at is using long division to divide polynomials. We'll use some synthetic division to divide polynomials. We'll evaluate a polynomial using the remainder theorem. And then we'll use the factor theorem to solve a polynomial equation. So what we are doing is we are doing some long division. So if we went all the way back to elementary school and we had something like 12 that we were dividing into 2, 8, 4, 5, 6. I'm making up some random number. I don't know if it goes in evenly or not. What we are going to do is go through the process of doing a division. So we are going to have a bunch of steps that are going to make no sense unless you kind of see what's going on. So I'm going to take it back to something nice and easy, what we already know. So example of, or step 1. Let me erase a little bit of this extra over here. All right, so step 1, arrange the terms of both the dividend and the divisor in descending powers of any variable. So the key part here is make sure that you're descending powers, highest power to lowest power. So you're going to set it up. You have your divisor on that outside, like the 12 is, and your dividend, that big crazy number in my case, on the inside. So step number 2 says to divide the first term in the dividend by the first term in the divisor. Just like you would do with regular long division, we have a 12. We obviously can't divide just into a 2. We have to divide into a 28. And we figure out how many times does 2 go into 28? Well, it goes in 2 times, and the location of that 2 would always be on top of that number that you used, right? That last number that we used 28. So the 2 goes above the 8. And then from there, so it says to divide the first term in the dividend by the first term in the divisor. The result is the first term of the quotient being the answer to that division problem. So in our case, that 2 on the top there is the first part of our answer, right? So step 3 says to multiply every term in the divisor, that number that's on the outside, by that first term in the quotient and write the resulting product beneath the dividend with like terms lined up. So very similar to back to elementary school, right? When you did your division here, you found that it went 2 times, and then you would take your 2 times 12, you would have your 24. So that was step 3, do the multiplication. Step 4 says to subtract the product from the dividend. So we would subtract, and we'd end up with 4 left over. Then step 5 says to bring down the next term in the original dividend. Well, in our case, back to elementary school, since 12 doesn't go into 4, we would have brought down that next number 4, and we would have started the process over again. So step 5, bring down the next term in the original dividend and write it next to the remainder to form a new dividend, and use this new expression as the dividend and repeat this process until the remainder can no longer be divided. This will occur with the degree of the remainder, the highest exponent on a variable in the remainder, is less than the degree of the divisor. As I said, it's a lot of words, but you're pretty much doing the process of long division. So you're going to take, in our case, we had that 12 divided into the 28. It went 2 times. 2 times 12 was 24. We subtracted. What was left over, we needed the next number brought down, etc. And then you would continue your process. So let's look at an example because, as I said, well, in a moment, this is a lot of words. I guess before we get to our example, we also have to talk about the division algorithm. It says if f of x and d of x are polynomials, as long as d of x is not equal to 0, the degree of d of x is less than or equal to the degree of f of x, there exist unique polynomials, q of x and r of x, such that, as I said, it's a lot of craziness. It'll make sense once we do an example. F of x is equal to d of x times q of x plus r of x. What does that mean? Let's go back to this ugly mess that we started, right? So if I took my 12 into 44, that would go 3 times, which would have been a 36, which would have given us 8, which bring down the 5. And then if I take 85 and I divide that by 12, that would give us 7 whole times. 12 times 7 is 84. Would have left us with 1. We'd bring down our 6. It would go in one more time, which would give us 12, leave us with 4. And then we would have said that we had some sort of remainder. Now, back in the day, you would have said R is 4, or you might have said that you would have had 4 out of 12 left over. That's kind of going to be a key point in this long division. So what does that mean in regards to this ugly mess? We had 12. Let me see if I can steal it this way. All right, so if I use this little example that we just did, right, our f of x, right, is what that crazy number on the inside of the radical was, right? And then we have a d of x, which is going to be the thing that's on the top, and multiplied by a q of x, and then we have a plus the remainder. So this is always going to be the remainder. So once we do a division, we have two things that were actually multiplied plus whatever was remaining is equal to that original function that we start with. So it says the remainder, r of x, equals 0, or it is of degree less than the degree of d of x. So it says also if r of x is equal to 0, we say that d of x divides evenly into f of x, and that d of x and q of x are factors of f of x. Again, a lot of words. Let's look at what this means when we go about doing this. So for an example, doing some long division, we are going to divide. We have 7 minus 11x minus 3x squared plus 2x to the third. We're dividing that by an x minus 3. So it says we begin by writing the dividend in descending order of x. So we have, obviously, we're dividing by an x minus 3 that goes to our outside. And if we take this ugly polynomial expression and we write highest exponent to the lowest exponent, that's where we have that 2x to the third minus 3x squared minus 11x plus 7. Now, a little thing to keep in mind. We had a third power, a second power, a first power, and this is technically x to the 0 power. If you were missing one of those exponents, you would want to fill in a plus 0x to that power that was missing. So something to kind of keep in mind for later on. In the meantime, these are all represented, so we're going to go ahead and start our division. So we have an x minus 3 that we are dividing into this ugly polynomial. So if I have an x minus 3, I have two terms, which means I need to divide into two terms. And what I'm going to do is I'm going to figure out what do I need to do to x. X times what gives me a 2x to the third? X times what gives me a 2x to the third? Well, x times 2x would give me 2x to the third. So just like what we did before with our division, when we divided that 12 into that 28, above the 8 is where we put that 2. So if I'm dividing an x minus 3 into two terms, once we figure that out, that 2x to the second power, we're going to write it above that piece. We're going to have a 2x to the second power, which if you think about it, this is an x to the second power, this is an x to the second power. So now, once I figure out x times what was 2x to the third, I now am going to take this piece on top and I'm going to multiply it by that x minus 3. So if I take a 2x squared and I multiply by an x minus 3, that's going to give us a 2x to the third minus a 6x squared. That means I need to subtract from that piece a 2x to the third minus a 6x. So if I'm subtracting that, I did that on purpose in parentheses, so that way I remember to subtract the pieces. If we have a 2x to the third minus a 2x to the third, those are going to cancel. If I have a negative 3x squared minus a negative, what happens if I subtract a negative? That means I'm really going to add 6x to the second. So minus 3x squared with a plus 6x squared is going to leave us with a positive 3x squared. And now I need my next piece to bring down. So I'm going to bring down this minus 11x. And I'm going to follow the same process. So if I have an x minus 3, I'm dividing it into a 3x squared. All I'm going to do is figure out x times what gives me a 3x squared. X times 3x. So I'm going to put a plus 3x up here. And I'm going to go about doing my multiplication. So if you need to multiply off to the side, 3x multiplies by an x minus 3 gives us a 3x squared minus 9x. So from this, I'm going to subtract a 3x squared minus 9x. And if I do that subtraction, 3x squared minus 3x squared cancels out. Again, a minus a negative means I have a plus. So a negative 9x with a plus, negative 11x with a plus 9x is going to leave us with a minus 2x. And again, we need to bring down that last piece, plus 7. So again, x times what gives us a minus 2x? We need a minus 2. So if I do that multiplication, that means we have a negative 2 that's going to multiply. I'm just going to squeeze over here. That's going to give us a negative 2x and a positive 6. So we have a negative 2x with a positive 6 that we have to subtract. So if I have a negative 2x minus a negative 2x, those are going to cancel out. A 7 minus a 6 is going to leave us with a 1. So that means I have a remainder of 1. So the quotient is, we end up with a 2x squared plus a 3x minus 2. But in order to write my remainder, I'm going to put a plus, and we had 1 left over. Well, 1 out of what? What were we dividing by? We were dividing by an x minus 3.